we'll be working on problem 6.17 from Griffiths Introductory to Electrodynamics, 4th edition. In it, we have a current flowing down a long wire of radius A. If the wire is made of linear material, such as copper or aluminum, with susceptibility chi m, and the current is just distributed uniformly, what is the magnetic field, a distance s from the axis? Find all the bound currents, and what is the net bound current flowing down the wire. Okay, so I already drew my Amperian loops right here. This one will be the outside case, and this one will be the inner case. So instead of starting with Beatz's law or Ampere's law, we can start off with the auxiliary equation because it is a modified form of Ampere's law, going as followed. I'll write this one in black. This is a path integral, closed path integral, h dot dl vector is equal to I free enclosed. Okay, doing this for the outside case first. So S is greater than A. Sloppy. S is greater than A. We have H times 2 pi S is equal to I free enclosed. So H vector is equal to I divided by 2 pi S, and this will be in the phi hat direction. And I can make this argument based on symmetry, knowing that it can't be flowing in the z hat direction, and it can't be flowing in the s hat direction, so it must be flowing in the tangential direction, excuse me. For the outside case, S less than A, same thing, closed path. I don't need to rewrite that. Okay, H times 2 pi S is equal to I, and in this we run into a sort of issue here. Since we're not even encompassing the entire wire, there's going to be a ratio between the section that we are enclosing in this small circle and the total radius of this wire. So we have to account for that as pi s squared divided by pi a squared. Pi's cancel out. This s term cancels out with one of these s's, giving us h vector equal to I s divided by 2 pi a squared, again in the phi hat direction. Okay. Going along, we can now solve for the magnetization. Let me go over here. Magnetization, m vector is equal to chi m h vector. For the outside case, simply substitute this in, and you get chi m I free is equal to 2 pi s phi hat when s is greater than A, and when s is less than A, we get chi m I s divided by 2 pi a squared in the phi hat direction, s less than A. Okay, now that we have magnetization and we also have the auxiliary, let's go ahead and find magnetic field. And since the question specifically says that we're given a linear material, we can use the equation for such a case where we have our magnetic field, our magnetic field B is equal to mu times the auxiliary field. And where mu is equal to mu naught, 1 plus susceptibility. Okay, plugging these in. So let's go for the outside case first. Magnetic field is equal to mu I divided by 2 pi s phi hat, mu naught. And now, my bad again. Again, this is S greater than A. And now for the inner case, magnetic field is equal to mu. And since we're inside the dielectric material, we substitute this mu for the mu naught I plus susceptibility I times S divided by, this is still free, 2 pi a squared, and in the phi hat direction. Okay. Field, let's go about finding the surface bound current and surface bound volume current. So I have equation for these, and I will go ahead and write these in black. For the surface bound, we have KB is equal to our magnetization cross n hat. In this case, since we're dealing with a cylinder, this would be in the S hat direction. And again, now for the volume bound current, JB is equal to chi m J free, but I don't want to use that equation. Instead, let's go about, since I decided to get the magnetization, we'll use the current, the curl. Okay, so going about this, we have, need to use red, because this is all dependent on whether we're inside or outside of the cylinder. Since we're dealing with KB, we're using the outer surface of our cylinder here, so our red. So this would be equal to chi m I free divided by 2 pi s in the phi hat direction cross S hat. And this is equal to chi m I free divided by 2 pi s. 2 pi s. Phi hat cross S hat is negative Z hat. Okay. Now for volume current, we now are using we're inside of our wire. So using this one over here, taking the curl, and we're using cylindrical coordinates, we have 1 over S, have S hat, S times phi hat, and Z hat. Taking the derivative with respect to S, phi, and Z, we have 0 S times our phi component, and 0 since there is no Z component. Going along, we have 1 over S, S hat 0 minus S phi hat, also 0, and only a Z hat, where ds S times m phi in parentheses equal to 1 over S ds s times chi m I free. Oh no. I free times s divided by 2 pi a squared. Z hat 1 over s derivative chi m I s squared divided by 2 pi a squared. Z hat derivative 1 over s of 2 chi m I s divided by 2 pi a squared. Z hat, stuff that cancels, these two, and s, oh, wrong color, giving us only chi m I, not 2, that's gone, pi a squared in the z hat direction. Okay. Total, our net bound current flowing down the wire, we're going to do this in black. I is equal to our JB times the area of our circle plus KB times the circumference of that circle. And this is the wire. We're no longer concerned with these. Well, no, we are, but the area and circumference that I'm referring to is respect to the wire. So substituting all of this in, JB, this one's GB, we have chi m I free divided by pi a squared times area of a circle, pi a squared, plus KB, there's negative. So this is minus instead of chi m I divided by 2 pi a. Wait, yeah, that should be a. Why is there an s? I'm sorry. And okay, yes, there's the reason why there's an s. Yes, there is an s. This s is greater than a. However, when we're now taking the surface, well, the surface of this is only of radius a. So this needs to be substituted with an a instead of the s, which is exceeding past this, past the area of the wire, and times the circumference, so 2 pi a, cancels, 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 and look at that, the total is equal to 0, and that makes sense because, oh, I'm forgetting z hats, well, in the end, it's still correct. Okay, and the reason why it's 0, this has to deal with the conservation of electrical charge, so the sum of this has to equal to 0 in order to maintain that. So, yeah, hope you liked the video.